This is week 1 of IC Design for Wireless Systems course. And in this week, we will be covering an introduction to what is a wireless system. And then we will move on to discussing about various architectures which can be used to design a wireless system. Okay, so to start, let me give a brief introduction to what is a wireless system. So, wireless system means, for example, let's say there are two people who want to communicate, and while they are trying to communicate, there is no wired or tethered connection between them, and it is a very practical situation. Correct? You don't expect that wherever you go, there will be a wired connection between you and another person whom you want to communicate with. So what happens is, when you want to exchange information, okay, certain this information can be a bidirectional exchange, then you need some messenger, okay, which can take this information from one place to another place. And when we talk about wireless systems, we find that since there is no wired or tethered connection, then we need to find a way where energy can actually act as a messenger and propagate and energy can propagate through the wireless medium. And this energy propagation is in the form of waves. So this can be either a sound wave or electromagnetic wave. For example, here let me show you this wavefront of energy, which is moving from point A to point B. And similarly, person at point B has created a disturbance. This disturbance is also, for example, propagating from B to A. So, in short, we can see that a wireless system is where you don't have any wired or tethered connection. So, no wired tethered connection. And this is very useful and very practical. For example, when we are in a mobile platform, okay, not stationary, and still we want to communicate with another person, definitely we cannot afford to have a wired or tethered connection. So you need to find a way to communicate wirelessly in such a situation. So what we do is we take advantage of waves to act as messenger of information. Waves means the propagation of some disturbance, some energy. When we talk about waves, based on our practical experience, we can easily understand that sound waves can do this job very efficiently, and because now itself, when I'm speaking, the microphone is kept at a farther distance, and I'm able to easily communicate whatever I want to say, okay, in a wireless manner. Sound waves will do this job. In addition to sound waves, any another very practical way to send information wirelessly is with the help of electromagnetic wave. Magnetic waves in the form of light, in the form of radio waves, you must have been already familiar. So this course is going to mainly focus on how to utilize this electromagnetic waves for exchanging information between 2 points in a wireless manner. Two waves can help in the wireless communication under different conditions depending on the physics behind their propagation. Okay, and we all know that electromagnetic waves has very good property that it can propagate even without medium. Okay, doesn't need medium. Effectively, it allows you to enable wireless system in space. Whereas you'll find that if there are some application which require these wireless systems to operate underwater, sound waves are very useful. Okay, mainly because the attenuation in the electromagnetic waves is much higher underwater compared to sound waves. In addition to that, we can also easily appreciate that the two waves have different speed of propagation, and also as they travel depending on the medium, they have different attenuation. So we will find that for most of the terrestrial and space application, this electromagnetic waves act like a very good messenger of information. So in the rest of the course, we will be focusing on how to utilize how to design circuits and systems which can utilize electromagnetic waves to enable wireless system design. The simple example which I have given earlier is looks like a bidirectional communication between two people at different location. So this is a type of wireless system which falls under the broad domain of wireless communication. Okay, so when we talk about wireless systems, we further categorize them depending on their application. Wireless communication is a widely known application of wireless systems. For example, our mobile phones is a prime example of how wireless systems are helping in communication with another person at a very far distance. Hmm? In addition to that, sometimes you may want to get a sense of some properties of an object or a target at a further distance without actually having any physical connection. Okay, so let's say you want to find the distance of an object without actually touching it. So you can do again in a wireless manner. This is called as ranging. Sometimes also called as sensing. Okay, and you might have already heard about this application, which is radar. So this radars allow you to do range estimate of a target in a wireless manner. There is another interesting application of wireless systems that involves trying to capture an image of an object which is at a far distance This is called as imaging. So the conventional imaging, you are already aware. With the help of a image sensor, you can capture the image and you can as well digitize the image data. But if we are trying to use the circuits and systems which are involved in this kind of wireless communication, wireless ranging, so you'll find that similar circuits and systems can also be used to finally control the illumination of a target at a distance. And then based on the reflection, we can recreate an image which is not visible in direct light. Okay. So it will be the image which will be visible at a different frequency. And this has again various application. One prime example is in the say millimeter wave security scanners, which are already deployed in many international airports. Now we have got some idea about what is a wireless system. So as to completely understand how a wireless system is designed and which all architectures we can realize what kind of signal flow will be present. Here we are attempting to build a wireless system from scratch. Okay. So that as we move along, we'll try to understand what are the practical difficulties and what we can do to solve those problems. Okay. So to start building a practical wireless system, first let us try to start with the simplest requirement. The simplest requirement can be in the form of some physical signal, okay, which is coming to a sensor. This physical signal, for example, can be sound waves, okay, which needs to be converted into electrical domain so as to later on transmit wirelessly. So what we need is we need a sensor and sensor interfacing circuitry. So the output of the sensor block is going to be in electrical domain, and this can be any physical signal. Okay, our case we can take an example of audio system. So the sensor effectively is a microphone. Okay, so you have sound waves and the sound waves reach into the microphone, and the output of the microphone is an electrical signal. And electrical signal means it can be voltage or current changing with time. And our job is to convert this electrical signal into electromagnetic waves which can propagate in the space wirelessly. Okay. So what we need is another transducer which then takes this electrical signal and convert it into electromagnetic waves. So this is how a very simple transmitter node of a wireless system may look like. Okay, we'll be having a sensor definitely to convert a physical signal into electrical domain, and then again we need a device which can convert this electrical energy into electromagnetic waves which can freely propagate in this space. What about on the other node where we are expected to receive this electromagnetic signals? So there also you can expect a similar kind of transducer setup, but operating in a reverse direction. So we want to receive these electromagnetic waves which have been propagating in the wireless space. Okay, and the signal needs to be first converted into electrical domain. The reason being, all the signal conditioning and signal processing, which we are already kind of familiar, can be easily implemented in electrical domain. So the transducer, it will be converting electromagnetic waves into electrical energy into electrical domain. And after that, our job is to again convert this electrical energy into some physical quantity. In our case, we can convert it back into sound waves with the help of speaker. Okay, the speaker can be acting as the actuator in this system. So we have seen a very simple wireless system where we are able to transmit sound wave from one node with the help of this wireless propagation of electromagnetic waves, and finally the same sound waves is being regenerated at another node. And this medium in which this wireless propagation happens is also called as wireless channel. Okay, so I hope this simple wireless system is clear to all of you. Now let us dive a little bit more deeper into the system. And first block which we see, which acting like a black box for us right now, is this transducer. Okay, so let us try to get some idea about what is this transducer and what may be the design specification and properties. Okay, so that accordingly we can optimize our system design. The transducer which we have talked just now, let's say this transducer which we are discussing is a passive transducer. Then in such a scenario, the same transducer can be used in transmission mode as well as in the reception mode. Okay, so here, just to emphasize this point, here we are doing wireless transmission. Okay, whereas downside we are doing wireless reception. Okay, and together these wireless transmission and wireless reception nodes are forming this wireless system. What I'm saying is, we can think of transducer which is passive in nature, so that the same transducer may be able to provide both functionality. So it can be reciprocal in nature, and it can, if it is converting electrical into electromagnetic waves, it should also be able to take electromagnetic waves and convert back into electrical energy. Okay, so such a transducer actually exists, which can do energy exchange between the electrical and electromagnetic domain, and this transducer is called as an antenna. Okay, so electrically it will look like this. So on one side we have electrical signal, the other side will be electromagnetic radiation. Okay, so electrical means the voltage and currents are going to be bound to the circuit, whereas on the electromagnetic side, the electromagnetic fields are going to propagate unguided in the wireless medium. This is called as antenna. Antenna is a transducer which converts energy between electrical and electromagnetic domain. As we can see in our wireless system, this antenna is going to play very important role, because this is only allowing the electrical signals to be freed from the circuit and propagate in the free space. Okay, then only finally it is only enabling the overall wireless system. So as we have seen, antenna is a very important element as it provides the interface between the electrical and the wireless channel. Okay, so next what we are going to do is we are looking into some of the specifications of the antenna and what trade-offs are present with respect to the practical size, the frequency of operation, and how efficient an antenna can. So if we talk about an antenna, so some of the important metrics which we are interested in will be efficiency, because it's acting like a transducer. Its frequency of operation, physical size. Okay. In addition to that, there are some other properties related to polarization and the radiation pattern. But for now, our basic discussion, we will just focus on these three important specifications. Okay. So it just turns out that if we go for a standard design of an antenna, which can be a dipole or a monopole kind of antennas, so you'll find that the three specifications which are written here are very tightly coupled. So let us just take an example. People dipole antenna. In the dipole antenna, we find that the size of the dipole has to be of the order of half of the guided wavelength of the electromagnetic wave it is interfacing with. Okay. And if we don't maintain this size, it turns out that the operation of the antenna, the transduction operation of the antenna is not going to be very efficient. So it has to have some physical size to maintain good efficiency. And in this physical size, we can see that this parameter lambda g is actually relating the frequency of operation. Okay, so c is the speed of electromagnetic waves in a given medium, and if we are talking about air or free space, the c is going to be 3 into 10 to the power. So c is speed light, okay, same as the speed of the electromagnetic wave, and accordingly, so that is going to be constant. So accordingly, for a given operation, frequency of operation, we get a physical size. And if we talk about other structures also, need not be dipole, let's say monopole, again the dimensions are of the order of the lambda. Okay, we can take a different antenna design. Dimensions will be of the order of lambda. So let's say we are trying to send an audio signal, and that audio signal I am modeling as simple electrical source. Okay, this is the model of that microphone sensor, if you people remember, which is receiving an audio signal that I were modeled with a simple Thevenin voltage source, okay, which has some V in and it has some internal resistance, and this source is going to drive the antenna. And this antenna is going to accordingly generate this electromagnetic waves. On this side we have signal in electrical domain. Okay. So let's say we are talking about audio signal. So the audio signal, if it is at around 1 kilohertz, then accordingly we can easily see that this 1 kilohertz electrical signal is going to give rise to an electromagnetic wave, which is also to be at the same frequency, okay, of 1 kilohertz, because the antenna is a simple linear device. Okay, it takes the input and then converts to different form without changing its frequency. So now if the frequency is 1 kilohertz, we can easily see that the guided wavelength of such electromagnetic waves going to be following this relationship, which is 3 into 10 to the power 8 meter per second free space divided by 10 to the power 3 hertz, and this is going to be equal to 3 into 10 to the power 5 meter or 300 kilometer. Okay. So if the guided wavelength is 300 kilometers, we can easily imagine that even if it is a, let's say, a monopole kind of structure, which is quarter wave, still it is going to be of the order of hundreds of kilometers. Okay, that is just too big for an antenna to be practical for most of the applications. So, looking at this simple example, we can easily see that if you're trying to design a wireless system, such a wireless system, a simple wireless system, what we have just shown, where a sensor converts a physical signal into electrical domain, and the antenna converts electrical signals into electromagnetic wave. The for most of the applications, the frequency is coming out to be too low for the electromagnetic wave, which will give rise to very, very high size for the antenna, and this is just not practical. So the solution is we cannot just take the low frequency electrical signal which is present and feed it to an antenna and expecting that the antenna is going to be small and efficient at the same time. So what we may have to do is we may have to add a network in between, a two-port network. So here I am not showing the reference for the antenna separately. So it is many times it is dropped and it is understood that the antenna using the same reference as the electrical side. Okay. So what we need is a two-port network to translate this F low to F high before we feed it to antenna. So the frequency of the signal has to be changed, or I should say to translate input signal frequency. So this is really important. We want to convert from F low to F high. And in between, definitely we just by short circuiting, it won't work out. We have to add and do some signal processing here. The next job is going to be to figure out what kind of network we can insert in between, which can result in this frequency translation. Okay.